Okay, so this lesson is all about simplifying radicals, but in a little bit of a deeper way than you've done before. So just some vocabulary so that when we use it, you should be a little bit familiar with the radical symbol. But you know that there's more than just square roots. There's cube roots and fourth roots and fifth roots. And so that's determined by this number here, this n, which we call the index. And the number underneath the radical we call the radicand. Okay. So the first thing I want to point out is inherently, just like if I rate the number 5, you know that that's a positive 5. When somebody just asks you what the square root of 64 is with no sign in front of it, that would be a positive 8. When you see the negative in front of it, then you would say negative 8. If it has a plus and a minus in front of it, then you can use both signs with that value. As we change the index, the results will change a little. So here's a cube root. So remember, you're asking yourself what to the third power makes the number that is the radicand, which in this case is negative 27, and that would be negative 3 to the third power. Here we would be asking ourselves what to the fourth power would give us 16, which in that case would be 2, and because it has a negative sign in front of the radical, we know it would be negative. Notice with the odd index, because odd powers can still have negative results, we can have a negative inside the radical without any problem. However, with an even index and a negative inside the radical, we would be asking ourselves what to the fourth power equals negative 16, which gets a little deeper into imaginary numbers than we go in this course. And so we don't really have to answer that. That we're just going to have like no real value. All right. So notice when we had like the square root of 64, we knew that the answer was 8 and we understood it was positive. Here, there's a little bit more of a mystery because of the x. So I understand that we have the inclination to know like, oh, the sixth root of x to the sixth would just be x, because you would be saying what to the sixth power equals x to the sixth power, and that would only work if there was an x in there. However, we have to be really careful here because notice that we just said x to the sixth power equals x to the sixth power. And so what if x equaled negative 2? On this side of our expression, negative 2 to the sixth power would be equal to, let's see, 16 times 4, 64. But on the other side of the expression, negative 2 to the sixth power, notice it doesn't have parentheses, would be a negative 64, and those numbers aren't actually equal. So the way that we write this is only true when x is a positive value, okay? So in order to express that, we include absolute value bars here. We only have to do that when there is some uncertainty, okay? So notice that this one, x could be positive or negative, given that it's only to the first power, depending on what number you put in. But underneath the radical, the x was raised to the sixth power, that would always be positive. See how those don't quite match? So to dictate that this answer will always be positive and will never end up negative is when we use the absolute value bars. Okay? So looking at the next example, we can kind of think about this in two parts because of the multiplication property with radicals. So we're going to think about these two separate ways. Now this one is numerical. There's no x and there's no mystery. So I don't have to worry about the positivity or negativity of that. So the fourth root of 16 is 2. However, this other expression does have an x in it. So the fourth root of something to the 12th power would be that something raised to the third power. But now here's where I have to ask myself, when it was underneath the radical, x plus 3 to the 12th power, no matter what I plugged in for x, even if it was a negative, would turn out to be positive because this would be raised to the 12th power, which is always positive. Here, x plus 3 is being raised to the third power. So if x was a big enough negative and I made a negative inside this radical, it could end up being negative. So there's ways for this answer to be positive or negative. They won't match when it's negative because on the other side it was always positive. So in order to restrict this to be always positive and to make sure I don't include the negative values, I want absolute value bars around that quantity. Okay. All right, so one more here. We have xy squared all to the sixth power, so it's in a group. So the sixth root of something to the sixth power is just that thing. But again, we have to analyze what's going to happen. So there's two variables in this one, so we have to look both at x and at y. Here underneath the radical, the x and the y squared are part of a quantity that gets raised to the 6th. So whether these are negatives or positive, the overall quantity always ends up being positive. Here, the overall quantity could be negative. The y will always be positive because it's squared. But notice the x could be negative or positive and then would change the result depending on what it was. So again, we don't want the x to be able to be a negative because we want to just produce positives. So that x needs absolute value bars. All right, so that's the idea of how we're going to simplify radicals now, so you can see that they are a little bit different than maybe you've done previously. So here the square root of 49 is 7, and the square root of x to the 8th is x to the 4th. And it could be both positive or negative, so we really don't even have to worry about the result. For part B, I want the final answer to be negative, so this part should simplify to be a positive. And when I take the square root of something that's raised to the 4th power, I would get that same thing raised to the 2nd power. I don't need absolute value bars in this case for many reasons. It has nothing to do with this negative here, okay? This quantity would still have to be positive. However, there's multiple reasons why it's guaranteed to be positive. One reason, that it's squared and not to an odd power. Second reason, the a in here is also squared, and a squared plus 1 would also always be positive. So there's no need for absolute value bars. For part C, the 5th root of 32 is 2. The 5th root of x to the 10 is x squared, and the 5th root of y to the 15th is y cubed. I don't even need to analyze for if I need absolute value bars because this was a 5th root, so I don't have to worry about signs in odd-powered radicals. The square root of negative 16 is not a real number. If we were working with imaginaries, we'd say for I. Or we can just say in this case, not real. All right, we're going to look at example 2. And then at the end, I'll come back to the try these, depending on how much information that you feel like you need for the lesson. So here we have the 8th root of an to the 8th power. So the 8th root of an 8th power would just be this thing to the 1st power. But again, this quantity is not guaranteed to be positive. If a was negative, it could be negative. If n was negative, it could be negative, or it could be positive, depending on how they both work out. However, under the radical, because the multiplication was raised to the 8th power, that would have always been positive. So to guarantee that when a and n multiply each other, they're always positive, we are going to include those absolute value bars around that multiplication. I'm not going to do part B because it's the same as what we did previously up here, so there's no need to repeat it. For part C, I'm taking the 6th root of something to the 18th power, so that would leave me with that quantity to the 3rd power. And it is an even radical, so I do have to pay attention to absolute value bars. So underneath the radical, this quantity was raised to an 18th power, which guarantees that this would always be positive. When I look at my answer, it's cubed, and even though the y is squared and the y will always be positive, it's possible this quantity could be negative because it's 3 minus whatever y squared is. So I need to make sure that that quantity turns out positive and not negative. So the way I'm going to do that is I'm going to include absolute value bars around that quantity to guarantee that it's positive. Okay. Again, I'll come back to the try these at the end so that you can decide how you want to do that. The second lesson is on multiplying and dividing. So you guys can use the properties of radicals with multiplication and division, and luckily basically we are allowed to separate the radicals or do them. Sorry, I was scrolling through the notes to see. So you can see here that multiplying the radicals together is the same as if they were under one radical being multiplied together, and dividing them is the same as if they were under one radical being divided. So when I see the fourth root of 125 times 405 here, I could multiply them together and make a really big number. But if I did that, I have the fourth root of a really big number. And I'm literally just going to write that right now. And then when I'm trying to find the radical of something I don't recognize right away, I'd be forced to break that number up. And the way that number would break up would be 125 and 405. I know that because I got them from here. So instead, I'm going to think about them as already being under one radical together, broken up a little bit, and then continuing to break them up further to look for common factors. So I see here there's 4 5s and 4 3s. So in other words, another way to write this would have been like 5 to the 4th times 3 to the 4th. And the fourth root of each of those would give us a 5 and then a 3, which would then give us 15. So here 135x to the 5th, if I break up 135, so I can rewrite this as the cube root, and when I break down 135, I have a 3 cubed and a 5, and then I have x to the 5th. So 3 cubed is a perfect cube, 5 is not. And then when I look at the x to the 5th is x cubed times another x squared. So there is a perfect cube, but there's also a piece that's not a perfect cube. So notice what's outside of the radical based on the perfect cubes, and what's left inside the radical, is a 5x squared. Okay. And here, if we're looking at square roots, again, I can think about this all underneath the radical together. So if I break down 48 and I break down 50, and then I have like x to the 7th and y to the 6th when they're all combined together, and I'm looking for perfect squares. So there's perfect squares, perfect squares. Oops, that's not a 2. Helps if you can read your writing. And a perfect square with like a single 2 left over here and a single 3 left over here. So outside of the radical and inside of the radical, what I have left. And then x to the 7th means it has 3 sets of x squared in it, which I can bring out, and then 1 extra x. And y to the 6th has 3 sets of y squared. So then I have 20x cubed y cubed times the square root of 6x. And in this case, we'd want absolute values around something like the y, because notice in each of the original problem's radicals, it was guaranteed to be positive, yet once we simplified it, it was not guaranteed to be positive. X was never guaranteed to be positive because something had an odd power there, so I don't have to worry as much about the x. Right, now looking at the division problems, okay, I'm actually going to look at part D first. I actually like the way that's written because I see some things right away that I can simplify, and if you can simplify, that's great. And so I have x to the 4th over 8yz cubed, and I can actually apply the cube root if I want right now. So the numerator, having 4 x's, has a perfect cube and 1 left over. And then in the denominator, the cube root of 8 is 2. And the cube root of the perfect cube of z is z. But y, I can't take the cube root. Now, here's the idea. You have to rationalize the denominator like we've done many times before. And so pay really close attention to your index. This radical needs to have perfect cubes in it in order for the numbers to be removed from the radicand. So when I look at it right now, it has 1 factor of y. But what I need it to have are 2 more factors of y, so it'll make a perfect group of 3. This is the extra stuff that I want to multiply into that radical. I can do that as long as I do it in the form of 1, meaning I'm multiplying that same quantity to both the numerator and the denominator. So here I would have x and the cube root of xy squared, and then in the denominator I would have 2z and y. And nothing simplifies further, so I rationalized it and there's nothing left to simplify. In the problem here I have the same choices to make. Let's say I didn't simplify it. So this one I simplified first and then I rationalized the denominator. Let's say I chose to rationalize the denominator first. This works either way. Sometimes it's simpler in some problems than in others. It just kind of depends on what you're more comfortable with and patterns that you see at the beginning. So when I look at this original radical that's in the denominator, I have a factor of 7 and 2 factors of x, but they're in a cube root. So again, I'm looking for groups of 3 of the same factor. So the extra stuff I really need in there are these extra factors to make perfect groups of 3, which is the same thing as 49x. Okay. So now I know that in the denominator, these are the factors I have, and they're all under a cube root. So I basically have the cube root of 7 being cubed and x being cubed, which is going to simplify to 7x. In the numerator, I want to look at the factors there too, because I don't really want to multiply 189 times 49. That seems like a lot. So 9 happens to go into 89 21 times, and then 21 is 3 times 7, and 9 is 3 times 3. So what I have in the numerator is and then I have 2 factors of 7 here. So I have 3 cubed and 7 cubed, and then I have x to the 8th now. And so when I simplify this cube root, I have a 3 times 7, and then x to the 8th means there would be 2 sets of perfect cubes. That would be x to the 6th with 2 x's left over. And now this simplifies a little bit. 1x can cancel one of these. A factor of 7 can cancel. So I have 3x times the cube root of x squared. And there's no denominator, which meant I probably could have simplified at the beginning, but either way works. Okay. All right. So I'm going to go back. So depending on what you need, if you need to check with the try these for the simplifying radicals, then go back with me now and we'll look at a couple instances of that. Okay, right here the square root of 169 is 13, and the square root of x to the 4th is x squared, and it can be positive or negative. I don't need absolute values for 2 reasons. This x was guaranteed to be positive because of the 4th power, but the answer, having x squared in it, would also be positive because the x is being squared, and it also has a plus or minus, so it's already taking care of both signs. The next problem, as I simplify the square root of this quantity to the 4th, I would want that quantity squared. And again, I don't need absolute value bars. It's not because of this negative, okay? The negative in front means I would need this other part to be positive, but it already is guaranteed to be positive because that quantity is being squared. So it will always be positive, just like the original one in the problem. For part C, the cube root of 125 would be 5, and the cube root of a to the 6th would be a squared. And I don't need to worry about absolute values in this problem because it's a cube root, and in odd indexes or odd powers, the sign shows up as what it should be. And then lastly, the cube root of negative m cubed n cubed. So m and n would show up there, and it would be negative because the cube root of a negative is negative. And again, I wouldn't worry about the absolute value signs because it's a cube root and not something with an even index. I'm going to go down to these other try these here. I'm actually going to start with part B. So the square root of 36 is 6, and the square root of g to the 6th is g cubed. And here I would want absolute value bars because g cubed, when I think about that by itself, there's ways for me to pick numbers for g that could be positive or negative. But in the original problem, it was a g to the 6th, which would only be positive, and I have to make sure I don't end up with that negative there and give it extra values. That's why I'm including the absolute value bars. Okay. For something like part A, number 1 mistake, you cannot square root each part individually. So the square root of a squared plus b squared is not equal to a plus b. Okay. Try it with some numbers and you'll see that doesn't work. The square root of a squared times b squared is equal to a times b, and now we'd know we'd have to have that in absolute value bars. So multiplication and division properties of radicals are really nice. Those properties do not hold true for addition or subtraction. So we can't do anything with this the way it looks right now, but notice it is factorable, and if you factor this 16m squared minus 24mn plus 9n squared. So you'd want the factors to start with 4m to make the 16, and end with 3n to make the 9. And then notice they would make 12 and 12 in the middle, which would make 24 if they're both negative. So really, that is a perfect square, 4m minus 3n squared. So now we're taking the square root of this squared. So we would have 4m minus 3n is the quantity. Normally, I would put absolute value bars around that, but I don't need to because of the plus or minus in front. Since it's going to change positives to negatives and negatives to positives, it will end up having both quantities present. So those are the notes, and I expect you guys to come tomorrow with questions. I'll be checking your notes and answering all of the questions that you have.